Hello, everybody. Thank you all for joining me once again. It is January 5th. Today I'm going to be doing LeetCode problem 1161, maximum level sum of a binary tree. I only have about 20 minutes to work on the problem. I have something to do afterwards. So we'll just dive deep. Excuse me, I already made a mistake. Okay, given the root of a binary tree, the level of... Let me put on the timer first. Given the root of a binary tree, the level of its root is 1. The level of its children is 2, and so on. Return the smallest level x such that the sum of all the values of node at level x is maximal. The smallest level x such that the sum of all values of nodes at level x is maximal. Okay, so in this example, we're given this binary tree. We see that the level 1 sum is 1, level 2 sum is 7, level 3 sum is -1, and because level 2 has a sum of 7, we return level 2. And it says the smallest level x. So in the event that there is a level 1, for example, is 7 and level 2 is 7, it makes sense to return level 1. But if level 3, for example, is 15, if the sum is 15, then it would make sense to return level 3 because that has a greater max sum than level 2 and level 1. Okay, so the first thing I'm thinking is that we are going to have to traverse through the binary tree all the way to the bottom, all the way to the leaf nodes, because there could be some number that creates a greater sum than the other levels. And we can do this using a few different methods. One thing I'm thinking of is to create a queue where we store each node and each level, and then we go through the queue and we pop off each node within that level and then add it to a current sum. And then if that current sum is greater than the current max sum, then we update the current max sum, and then we update the current max level. But it has to be greater than, it can't be equal to, because if one level has, like I said before, 7 and the next level has a sum of 7, then we don't update it. It has to be greater than the max sum. So that's pretty simple. So for example, let me create some notes. So we iterate through the tree starting at level 1, which has node 1, and we add that sum, something like we can create a variable called current level sum equals to the sum of the values of each of those nodes in that level, which in level 1's case is 1. And we would also need a max sum, which currently equals to 0. And then we would need a max level, which would be, we could just say float -infinity, because initially there isn't a max sum. And given that the number of nodes is between 1 and 10 to the 4th power, there is guaranteed to be a max sum. So in that case, I could just say float -infinity. And then once we get to the first node, that value is updated to the first level. Okay, so at level 1, we have one node. We take the value, which is 1, and the current level sum is now 1, which is greater than the max level, or excuse me, the max sum. So we update the max sum, and then we update the level, which would be level 1. And then after we do that, well, this one has been added to a queue, and then we would get the child nodes of that node, assuming it has child nodes. So this is popped off, node 1 is popped off. We add it to the current level sum, update these values, and then with that 1, does that 1 have child nodes? It does, 7 and 0. So let me see if I can, a visual element to this always helps. It has nodes 7 and 0, and so those nodes get then appended to the queue, 7 and 0. And then we can traverse once again, popping off 7. Current level sum gets updated after, or I'm sorry, it gets reset to 0 after each iteration of the queue. So we pop off the 7. We add it to a current level sum, which is 7. And then we append the child nodes of 7 to the queue. In this case, it would be 7 and negative 8. And one small thing is that before we do the iterations, we need to track the length of the queue before we've appended those values, so that we don't accidentally pop off a node in the queue more than, or pop off a node in the queue that isn't within the same level. So we would need to say the length in this example is 2. So we would create essentially a loop that is that loops from 0 to 2, popping each of these values, and then once you get to 2, it would be an empty queue. Okay, so we pop off the 7. We've added the current level sum. We don't yet add, or we don't yet compare the current level sum with the max level, because we could potentially have a negative 1,000, and then therefore we wouldn't have a greater max level sum. So, but we do append the child nodes, 7 and negative 8. And then we pop off the 0, update the current level sum, which is 0, and then we append the child nodes of 0. In this case, there aren't any. And then we compare it with the max level sum. That gets updated to 7, and the max sum gets updated to 7, and the max level gets updated to 2, because this new level has a greater max sum. And then lastly, so we see, let me see if I can get these over a little bit. And then 7 has the 7 and negative 8. Just never ignore that period. Okay. Current level sum gets updated to 0. And we pop off the 7. We take its child nodes if it has any, and it is a leaf node in this case. So we just add it to the current level sum, which is now 7. So that's been popped. And one additional thing is that we are popping from the front using a deck data structure instead of popping from the right to the left, like a stack essentially. And we do that because in the example of level 1, when we previously had 0 and then we had appended 7 and 8, we popped from the front because if we were to pop from the back, then we would get the child elements, or the child nodes of 7, instead of staying on that same level. So that's an important distinction. So now we've, let's go back. Now we were previously at -8, and that got popped. -8. Current level sum gets updated to -1, and we see that it is not greater than the max level, or greater than the max sum. Therefore, the max level remains to be 2, which we see is the case in the output for example 1. Another important thing is that we will have to have a variable that keeps track of whichever level we're on, initially set to 1 and not 0, as one could potentially make that mistake. So initially the level is 1. And then, yeah, we have the solution of 2, and then we just return the max level. So we will have to iterate through the entire binary tree, but I believe that is the most simple, and it is an efficient method to getting the max level sum, or the max level. So now I will implement that. So we do need to import the collections library, and then we'll have to create the variables max level sum. We'll just say max level, and max level sum equals to float -infinity and initially 0. Not 0, actually. Float infinity again, because if we were to have a root value of -10, for example, then it wouldn't make sense to have a max level sum of 0. We need it to be updated for whichever number we see that's greater than float -infinity. Secondly, we'll have a q equals a dec, and then we will initially store the root. Okay, and then we will say while the queue exists, we'll get the current length of the queue. We'll get the current length of the queue, and it's important we do this inside of the loop instead of outside, because we need to get the current length of the queue. Okay, and then we'll say for this is just, we don't actually need the value in here. Yeah, we don't need the value in there. For in range, okay, in range length, then we'll say node equals q dot pop left, popping the first element, and then we also need a current level sum equals to 0. We'll say the current level sum plus equals the node dot value. If node dot left, q dot append node dot left. If node dot right, q dot append node dot right. Okay, now we've reached the end of the length of the initial queue. As I mentioned before, this could, in level 2, this would be 2. So we've stopped -7, -8. Once the last queue gets popped off, these nodes still remain because we know the length of the current level we're on. So we'll say if current level sum is greater than the max level sum equals the current level sum, and then we also update the max level equals to current level. Current level initially equals 1, and then regardless of that, we will have to update the current level, and then we return the max level. Okay, so this looks good. This is initially float negative infinity. We're guaranteed to have at least a root node based off of the constraints given. While queue length equals the length of the queue, which is initially 1. Current level sum is 0. Okay, we iterate the length of the queue. We pop off the root node, which is 1. Current level sum plus equals to 1. If node.left, queue.append the nodes to the end of the queue. If the current level sum is greater than the max level sum, then the max level sum gets updated and the max level gets updated. So that would update to 1. Okay, and that looks great as well. Max level sum gets updated. And then the current level gets updated as well. And then once we go through the queue again, current level sum gets updated to 0. And then we return the max level. That all looks great to me, so I think that I will run the program. Okay. Excellent. This algorithm will run in O of n time because we will have to iterate through each node, and the space complexity is also O of n, which is the space for creating the queue, which stores every element or every node in the binary tree. Well, that's it for tonight. I hope you enjoyed my process, and keep on working towards your goals, everybody. Thanks and take care.